Here's the question I asked at the end of the previous part of this lecture. Notice that Morty and Rick have their y-axes pointing in the same direction, and so they should both agree that the y coordinate of position is increasing, or in other words, that Vy is positive. However, Rick's x-axis is pointing in the opposite direction to Morty's, and so he will come up with the opposite sign for the x component, and so he will get A. Just as it can be very useful to represent a motion using a position versus time graph like this x versus t, it can also be very useful to represent it using a velocity versus time graph, or rather a velocity component versus time graph. And this motion we've been looking at is very easy to do that with just conceptually. So first of all, I'll note that we can divide this motion into roughly 5 parts. From about this time earlier, the card isn't moving. It has a 0 velocity. And we can see that by this horizontal line in the x versus t. Then x increases, and so Vx is going to be positive for a while. And then again, the card is stationary, and then it moves back in the other direction, so Vx will be negative with our choice of axes, and then Vx will be 0 again. And so roughly, if we calculate the velocity over any time interval in here, it's going to come out 0. If we look at any time interval in here, no matter which ones we use, we're going to get roughly the same answers for Vx, because that's a straight line, and that's indicating a constant v. So throughout this time period, the Vx versus t graph would be constant and positive, and then it would be back to 0, and then again here it would be Vx would be negative, and then back to 0. And the only complicated times are when there are curves here and it's doing some sort of transition, mostly because I'm pushing on it with my hand, and so it's a more complicated motion in there that's harder to model. It may seem like the speed is always just the size of the velocity. The velocity is basically just a speed with a direction. And a lot of the time that's true, but when you're talking about average speed and average velocity, there can be a subtlety, and this is a good example. So here are 2 times that I've chosen and just arbitrarily called them my initial and final times, and I've given you the x component of position at each. So we can now easily calculate the average x component of velocity over this time interval, because clearly the x component of the displacement is negative 0.4 meters. And so that gives us this average x component of velocity, negative 0.067 meters per second. Now, does that mean that the average speed over this same time interval is just 0.067 meters per second? Well, no, it doesn't, because remember, to calculate a speed, you need to take the distance traveled over the time taken. And the distance traveled isn't 0.4 meters, because the cart went out to this point where it stopped and then turned around. So it went about 0.55 meters to the right, stopped, and then went about 0.95 meters back to the left. And so the total distance traveled is 0.55 plus 0.95 meters, and that gives us a totally different average speed. Let's just finish up by looking at something that now the abstract level of working with equations can get us. So here's our definition of the x component of the average velocity. And remember, we can think of that just as a slope of the x versus t graph. Suppose the velocity is constant, then Vx at every moment is the same, and it's always the same as Vx av. So we can just drop the av and say Vx is delta x over delta t. And that's only for a constant velocity. Now let's just rearrange. Multiply through by delta t. Realize that delta x is a final minus initial. And let's take the xi over to the other side. And finally, I'm going to say, let's think about the case where ti is 0, and we're going to simplify things by letting whatever later tf we're thinking about just be t. There. So what? Well, here's what. Here's the x versus t graph. We know it's a straight line for constant velocity. And at t equals 0, xi is there on the graph. And vx, we know, refers to the slope. But doesn't this seem awfully familiar? It's the equation of a straight line in disguise. And so what we're really seeing here is that if you know xi and vx, then I can give you any t and you can tell me the value of x. We've got x as a function of t. And that's going to be handy to us.